Alright, welcome back everyone to section 2.3, Interpretations of the Derivative. Today we are introducing Leibniz notation. Alright, so far we have seen what we call function notation. So far we've seen function notation. There we go. Alright, and we know that looks like f prime or f prime of x or something like that, right? Alright, so that's what we've been seeing. We also know that the derivative is approximated by the average rate of change over a small interval. We also know that the derivative f prime of x is approximately our change in y over our change in x, right? So Leibniz notation is meant to remind us of this approximation. Alright, so if we have y is equal to some function of x, then we write the derivative as dy over dx. Alright, so we can think of this d out in front here as the delta, or the difference in a change of values. Alright, so it's not extremely different than what we've seen before, right, if we're using our delta notation, but here this is called Leibniz notation. So just the individual parts dy and dx, without being in the fraction together, don't have much meaning on their own. Alright, so dy and dx don't have any meaning. Alone. Alright, so really we should think of our dy dx as one symbol. Meaning everything should come in a package. It's a package deal, right? So dy and dx always come together. Even better, even more formal, would be to think of it written like this. So even more formal would be to write like d over dx of y. Okay? So this is read as the derivative of y with respect to x. Okay? Again, where d over dx is a package deal, is one symbol. Okay, so this type of notation is helpful when trying to figure out units. Okay, for example, if we recall that s is equal to f of t is our position function. Alright, our position function for a moving object at time t. Then v is equal to f prime of t is the velocity. Meaning how quickly is our object changing position. Alright, almost there. So if we write our velocity derivative In Leibniz notation, we have v prime, or I'm sorry, s prime, which is equal to v, is ds over dt. Alright, so written in this notation, this reminds us that we have a change in position. Change in position, remember that was our s, and over a change in time. So our units here would be position over time, or distance over time. And we know that is true for our velocity function. Alright, the only quote-unquote disadvantage of our Leibniz notation is it's a bit awkward to specify the value that we are evaluating at. Alright, so to specify a value to plug in the derivative in our Leibniz notation, we would say dy dx or ds dt, whichever variables you're using, and we write this long bar, okay, and we read this bar as the words evaluated at, that's a t, evaluated at, and then we'd write what we are evaluating it at. X is equal to 2, for example. Okay, so this is how we would specify that value. Obviously, function notation is a little bit simpler, right? So this is our Leibniz notation. And to specify the same thing in function notation, we would just have to write f prime of 2, right? So it's a little clunkier in the Leibniz way, but again, it has its pros as well, so we can help with our units and everything. Alright, so with that, we're going to finally get to our first example today. So the cost C in dollars of building a house the size of a square feet is given by this function C is equal to f of a. What are the units and the practical interpretation of the function f prime of a? Alright, so let's go ahead and rewrite our derivative in Leibniz notation. So we have f prime of a. Well, that is going to be the derivative of the cost with respect to the area. Okay? So, for our units, our cost is in dollars. We have dollars over, and our area is in square feet. So there we've went ahead and written our derivative in Leibniz notation, and it has helped us figure out our units. Alright, so what is the practical interpretation of this problem? Well, you can think of the difference in cost, so our DC, as the extra cost of building an extra square feet of the house. So, if you are planning to build a house with a square feet of area, the derivative f prime of a is approximately, I'll just say approx, so approximately the cost per square foot. of the extra area involved in building a house. One square foot larger. All right, than you were maybe originally planning. If you remember, this is called the marginal cost. The cost it would take to increase production by 1 unit, in this case increase the area by 1 square foot, that is our marginal cost. And so our derivative, which is our change in cost over our change in square feet, that's going to give us how the amount of money you would need to add to your budget in order to increase the size of your home. Alright, so let's get to example 2. Thank you very much for that reminder. Okay, so example 2, we have Sam's puppy, whose name is Meatball, has the weight function W is equal to G of T, where W is in pounds and T is Meatball's age in months. So question A asks, do you expect G prime of T to be positive or negative, and why? So if we think about it, G prime of T, this is the derivative of the weight function, right? Derivative of the weight function. And what does the derivative tell us? How quickly something is increasing or decreasing, right? So, derivative tells us how quickly something is increasing or decreasing. Okay, so Meatball is a puppy. Okay, so a puppy is still in its growing phase of becoming a full-grown dog. So do we expect his weight to be increasing or decreasing? If we expect his weight to be increasing, it would make sense that our derivative is positive. So we would expect our derivative to be positive since Meatball is growing. Alright, so his weight should be increasing. Alright, part B asks us to write the derivative in Leibniz notation. And it asks what are the units of our derivative. Alright, so we need to write G prime of T is equal to, well, it's our derivative of our weight function with respect to time. So we have dw dt. Okay, our derivative of our weight with respect to time. So, for the units, weight is measured in pounds. So we have pounds over time, and in this case, time is months. So we have pounds per month is our units for our derivative. Alright, part C asks us to interpret G prime of 8 being equal to 6 in the context of this problem. And then what are the units of the numbers 8 and 6 in the equation? So let's see here. We have G prime of 8 is equal to 6. So let's see. G prime of T was our derivative, so 8 is our t value, and 6 is going to be our output, which is our weight values, right? So we have 8 months, that's our unit for 8, and 6 pounds is what we have for our unit for 6. Okay? But we still need to interpret this equation. So our derivative, again, is telling us how quickly something is changing. So in this case, meatball is gaining weight, or let's see here, at the age of 8 months. Here we go. Meatball is gaining weight because it's positive, right? So that means it's increasing at a rate of 6 pounds per month. That would be our interpretation in this equation. Alright, so assuming the meatball is healthy, what value do you expect, say, g prime of 36 to take, and why? Alright, so let's think about this for a second. 36 months, well, that's 3 years. So in 3 years, Meatball is no longer a puppy. He is now a full-grown dog. Okay? So, do we expect his weight to be changing much at all? Do we expect him to be gaining weight or losing significant amount of weight if he is healthy, as the question specifies? If he is healthy and he is fed on a regular basis, we would expect Meatball to stay at a steady weight. Okay, after reaching his full-grown adult stage. So, how can we represent that? If his weight is not increasing, nor is his weight decreasing, his weight should be staying constant. So, the amount of change, the rate of change of his weight at 36 months should be near 0. Alright? Maybe it will increase a little bit or decrease a little bit here and there, but overall it should stay about 0 for a healthy dog. Alright, so now we're going to look at a new concept using tangent lines as estimations. And maybe you haven't seen the word tangent line spelled out yet, but this is what we've been doing. Every time we go ahead and take a point on our graph and we draw a line through that point. Alright, so in this case, our red line, this is our function f of x is equal to the square root of x. And this black line here, I'll give you the equation of the line. It's 1/2 x plus 1/2. Okay? And this is our tangent line at the point x is equal to 1. Alright? So, and what we know, the relationship, okay, between our function and this line is that the derivative of our function f of x is the slope of the tangent line. Alright, that's an important concept. So the derivative of our function is the slope of the tangent line. Okay, in this case, our tangent line is at the point 1. We could also have a tangent line at the point 1/2, which would have a different slope, right? Instead, we're going to look at this one. All right, we are going to look at this tangent line through x is equal to 1. And why we're interested in this is that we can use tangent lines to approximate or estimate values of our function. Okay, so what we notice about our graph here is that near our point x is equal to 1, which is right here, x is equal to 1, nearby, I'll go ahead and say roughly here to here, our function and our derivative line match really well, don't they? They almost overlap perfectly. So, if we used our tangent line to approximate any values in this range, it would be a really good approximation. But if we start looking out further over here and further, it's not going to be as good as an approximation. All right, so let's go ahead and plug in some values and see how this works out. All right, so we have a little table down here where we're just going to plug these values into our equation of the line and then our function to get the real and approximated values, and then we're going to subtract them to find the error or the difference, okay? So at x is equal to 0, we have, oops, I need my black pen, f of 0, well that's the square root of 0, which is 0, so the actual value is 0. Alright, and then we have y is equal to 1/2 times 0 plus 1/2, so that gives us 1/2. I'm going to go ahead and write these in decimals, so we have 0.5. So 0.5 minus 0, well that gives 0.5 as an error. So we have a whole half a unit of error between our approximated value and our actual value, and we see that this is not a very good approximation at x is equal to 0, right? But let's go ahead and keep going. So I'm just going to go ahead and fill out the rest of this table. Alright, you can just do these calculations with a calculator, alright, or with a few minutes. So at x is equal to 1/2, we have 0.7 is our actual value. Our approximated value is 0.75. Alright, so we got a little closer there. So our error is only 0.05. At 1, and this is the value at which we drew our tangent line, our actual value and our approximated value match up because that's where we drew our line. So we have no error right there. At 1.5, our real value or our actual value is 1.22. Our approximated value is 1.25. So our error is the smallest we've had other than our perfect approximation, which is 0.03. And then at 2, we have 1.41, 1.5. So our error is 0.09. All right. So we can see that our error, I'm just going to move this over here. Error is smallest closer to the point where the tangent line was drawn. And just to emphasize this even more, I decided we'd calculate x is equal to 10 just to see what happens. We don't see it on our graph at this point. but we can see that our tangent line is going to keep going up, and our red line of our graph, the square root of x, is going to kind of level out a little bit. So we can expect it to be pretty outrageous. So our actual value is going to be 3.16, and then our approximated value ends up being 5.5. So yeah, we are nowhere even close with our approximation now. We have an error of 2.34. Alright, so this is how we can use our tangent lines as an estimation or an approximation for our function values at certain points. However, we now learned that you can really only trust it in a smaller window and not too far away. Alright, so let's do example 3. We have that fertilizers can improve agricultural production. A Cornell University study on corn production in Kenya found that the average value, y is equal to f of x, in Kenyan shillings of the yearly corn production from an average plot of land is a function of the quantity of fertilizer used in kilograms. Alright, so our first problem is we need to interpret the statements f of 5 is equal to 11,500 and f prime of 5 is 350. So let's tackle that first piece. F of 5 is equal to 11,500. So this tells us, so let's see, f of 5 is equal to 11,500. Our function is f of x, so 5 must be x, alright, which is the quantity of fertilizer in kilograms. So we have 5 kilograms of fertilizer. Okay, and 11,500 is our output, it's our y value, and that's going to be the shillings worth of corn. Okay, so the amount that they can sell the shilling or sell the corn for. Shillings is the currency in Kenya. Alright, so our 11,500 is our y value. Okay, and that's going to be the 11,500 shillings worth of corn. Okay, so our full interpretation is that 5 kilograms of fertilizer means that 11,500 shillings worth of corn can be produced. Alright, so we interpreted the statements for f of 5 is equal to 11,500, but now we need f prime of 5 is equal to 350. So remember, our derivative is the rate of change. Alright, so we have dy over dx in our Leibniz notation is 350. Okay, so this means, or evaluated at x is equal to 5, there we go. This means that if the amount of fertilizer increases by 1 kilogram, then corn production will increase, gotta give a little bit more space, increase by 350 shillings. Alright, so now we need to use this information to fill out part B. So we need to use the statements in part A to estimate f of 6 and f of 10. So we know f of 5 is our 11,500. And we also know that if we increase 1 kilogram of fertilizer, we are going to increase the shillings worth of production by 350. So F of 6 means that we are increasing our fertilizer by 1 kilogram. So we should have our original shillings production plus 350. Okay, so we should end up with 11,850 shillings worth of corn. Now F of 10, we are now increasing by 5 kilograms worth of fertilizer. So we need to start with our F of 5, which was our 11,500, and then add 5 times our 350 shillings worth. Alright, and so in this case we should get 13,250 shillings. And these should all be approximations since we are using our tangent line here. Okay. Part C asks, which estimate above is more reliable? Well, we learned earlier that the closer we are to the original value, the better the estimate is. So in this case, we estimated f of 6, and then we estimated f of 10, where our original value was f of 5. So f of 6 is the more reliable estimation. Alright. So then we have example 4. A company finds that it costs them $4,250 to make 20 items. They also know that after making that many items, it costs them approximately $25 to make another one. What are the values of C of 20 and C prime of 20? So, in this case, this is asking us what is the cost of 20 items. That's what the first question is asking. And then the second one is asking, what is the price increase or decrease, but the price change, I guess I'll say, after or at 20 items. Okay, so what is the cost of 20 items? Well, our question tells us it costs them $4,250. So C of 20 is $4,250. And then what is the price change at 20 items? What I mean by that is how much is the price going to change from 20 items to 21 items, and so on and so forth. So that would be our derivative. Alright, so C prime of 20 is our rate of change of the price at 20 units, which our question says it's going to cost them $25 to make another one. Alright, so C prime of 20 is 25. Part B asks us to use our answers from Part A to estimate C of 18, C of 23, and C of 30. Alright, so C of 18, well, we're starting at C of 20, which is our 4,250, and we need to subtract 2, because we're dealing with 2 units. But what is the cost of 2 units? Well, the cost of at least 1 unit was 25. So we need to go ahead and say 2 times 25. So we'll end up with 4,200. Then we have C of 23, okay, where again we're starting with our 4,250, but this time we're increasing from 20 to 23. So, we are adding 3 times 25. Alright, so then we'll end up with 4,325. And then lastly, the cost of 30 items. If again we're starting at 4,250, and now we're increasing by 10 times 25, we'll end up with 4,500. Alright, and this question doesn't ask it, but I'll go ahead and pose it to you. Can we trust C of 18 more than we can trust C of 30? Or the other way around? Again, C of 18 is closer to our original value than C of 30 would be. So this would be the most reliable approximation, because it was the closest to C of 20, which was our original value that we were working from. Alright, and that wraps up section 2.3. Don't forget to take the comprehension quiz, and I'll see you in the next lecture.